Let's get started. So, when you solve a logarithm, what are you solving? Like if you were at a math party and somebody asked for a one-word synonym for the word logarithm, what would it mean? What are you solving for? You're solving for the exponent. So logarithm is ultimately just a fancy word that means solve for the exponent. So we're starting out with simple questions like 2 to the x equals 50. And ultimately, we just want to solve for x when x is in an exponent. This creates a whole field of mathematics unto itself. And we talked about approaching a problem like this by using the sandwich technique. That was our first thought, is let's say I wanted to know what 2 to the x equals 50 was. So I'd start by writing down 2 to the x equals 50, and then I would think of a fact that I do know. So for instance, 2 to the 2, 4, 8, 16, 32. So 2 to the 5th is slightly smaller than it. And 2 to the 6th is 64, slightly bigger than it. And so I've created a sandwich. I know my answer is 2 to the 5 point something. So then I start guessing. I say, well, it could be 2 to the 5.5. And then I would use my calculator and start coming up with guesses as to what my answer could be. So 2 to the 5.5 is 45.25. And that's too small. So I would try 2 to the 5.6. And let's see, that would be 48.5, getting closer. And then 2 to the 5.7 would be, 51.98. So now we started with one sandwich between 2 to the 5th and 2 to the 6th. I now have another sandwich between 2 to the 5.6, sorry, 2 to the 5.6 and 2 to the 5.7. And you just keep going like that. How long does that process take? Yeah, first of all, psychologically, it feels like it takes a long time because you're sitting on your calculator and you're just trying things randomly. But also it takes infinitely long time because if you want the answer, it's going to be infinitely many decimals. And so you'd be doing the sandwich technique infinitely many times. So ultimately what we'd really like is a way to solve for an exponent without doing all of that work. And ultimately, well, hold on, I'll stop right there. Anyway, that's what it means to do a logarithm. A logarithm means solve the exponent. You can do it by brute force. It's not very exciting. So instead we're going to develop all sorts of techniques that allow us to solve for an exponent by using one of two buttons on our calculator called log and ln. Okay, let's keep going. How do you read the expression log 216? How would you read that?
Log base 216.
Yeah, very good. So first of all, just reading it straightforwardly in English, you would say log base 2 of 16. So this would be log base 2 of 16. And the key words there are base and of. So you'd read log base 2 of 16. Sometimes I hear people say log 216, and it's just too confusing. Because did you mean log 216, or did you mean log 216? Right, that leaves a little ambiguity. So we would always say log base 2 of 16. So that's how you'd say it in English. But now, what does it mean? How do you read this as a question? Yeah, perfect. Very good. 2 to the power of what? Or 2 to what? 2 to the power of what is 16. So we're really saying 2 to the power of what is 16. And a question like this we can answer off the top of our head because it's 2, 4, 8, 16. So the answer is 4. So 2 to the 1 is 16? 4. So that's how you read it in English, and that's how you read it as a question. Okay. Convert 3 to the x equals 81 into log form. So first of all, let's just look at that. 3 to the x equals 81. That would be exponential form. 3 to the x equals 81. That's exponential form because there's an exponent. So if there's an exponent, then you're in exponential form. So, and what we really have here is base to the exponent equals the answer. So that's exponential form. I'm going to hold off on converting it for a second. Now, how about, well, no, okay, we can just go ahead and convert it. So how do we convert 3 to the x equals 81 into log form? Yeah, it'd be log base 3 of 81 equals x. There's a couple things to notice about that. One is maybe I should have, well, here, let me finish doing this. So this is log base b of the answer equals the exponent. And perhaps it'd be helpful to see those two expressions stacked on top of each other. So if you have base to the exponent equals the answer, then that becomes log base b of the answer equals the exponent. And so when you convert between forms, you'll notice that the b stays the first value, whereas the exponent and the a switch sides. And what's most interesting about this then is you can just look at this expression right here. What is log base b of a equal to? An exponent, which is what we're saying logarithms solve for. When you solve for an exponent, you're solving a logarithm. And in fact, log base b of a, that whole expression right there, is simply equal to the exponent. Okay, so there we go. That's the two different log forms. That's how to convert. And then finally, on our calculator, what does the button log actually mean? When you hit the log button, it's really log. Right, it's really solving for a base 10. Log is really log base 10. So on your calculator, log all by itself without a number there means log base 10. The 10 is assumed. So log really means log base 10, which means you're solving a equation of the form t to the x equals n. And also remember we said that that n value always has to be positive. Because it's an exponential graph which has an asymptote approaching the x-axis. An exponential graph will never hit the x-axis and it will never go negative. It will always be positive. So we can only ever solve problems like 10 to the, or an exponential expression equals a positive number. All right, so then what is the ln button? What is that button? Yeah, that's going to solve e to the x equals some number. This is really, ln is really log base e. And e is a number that we don't come across too often in society. We come across pi all the time, 3.1415, whereas e is 2.718281, etc. And it's a number that is associated with natural growth processes and natural decay processes. And so that's base e, and that's when you're solving an equation like e to something equals positive. And I didn't have a question up there about it, but let's talk about domain exclusions real quick. What can you not take a log of? So let's just review real quick here. Domain, we know that we cannot divide by 0. We know that we cannot square root the negative. So what can you not log? You can't log a 0 because that would be undefined. And what else can't you log?
Negative.
A negative because that would be imaginary. It's pretty interesting to note that it's for the same reason. So you can't divide by 0 because that's undefined. Divided by 0 isn't imaginary. It's just undefined. Whereas square rooting a negative is imaginary. It's not undefined. It's imaginary. And log works the exact same way. If you try to log a 0, that's undefined on your calculator. And if you try to log a negative, it'd be imaginary on your calculator. So there's some nice symmetry there. And moving forward, as we do domain tests, we'll test all 4 of those. Although it's not like you have to do 4 separate tests. What you do, recall, is whatever the denominator is, you'd say, I don't want my denominator to equal 0. So that's that test. And then for the radicand, you don't want your radicand, well, you want your radicand to be greater than or equal to 0. So that's another of your domain tests. And then for this one, we call the number inside the log the argument. Not like a bad conversation you had with your spouse or parents, an argument, but the argument of a function, meaning the input. So for the logarithm, you'd say, I want my argument also to be greater than or equal, well, no, not greater than or equal to 0, just strictly greater than 0. The argument of a logarithm has to be strictly greater than 0. It has to be strictly positive. Okay, so those are our 3 domain tests. That's everything we talked about last time. And everybody ready to rock and roll, learn more about logarithms? I'm sure that over the weekend you felt a little distracted. You really couldn't focus on just enjoying your free time because you kept thinking about logarithms. I wanted to get back here on Monday and keep studying logarithms. I totally get it. Okay, let me go back here. Those were one of the questions. As we ended class last time, we just started the Chapter 6 packet. So let's just see where we are here. Today is April 1st, and we've got this week to study logs. And then next week on Monday, I'll take your test on Chapter 5 and 6. By the way, did everyone take their practice test? Did everybody take it? Isaac, I think you need it, because here you go. There's your practice test. And do you have your Chapter 6 notes? Yes, you do. Did everyone get a practice test? There you go. Curious? Anybody else need the practice test? Okay, the practice test is also posted online on Canvas announcements, as well as all the solutions. So I solved the entire practice test. I wrote out solutions. It's posted online on Canvas under announcements. Oh, yes, Raj? Oh, I'm very sorry. All right, so that's where we're at. We've got this week to study logs. Anything else? I think that's it. Well, I think I already told you these jokes.
Yeah.
Oh, darn. Well, let me think of a joke by midway through, and I'll tell you a new one. Okay, so we just started looking at the packet. So everybody just turn to the first page of 6.1. You'll see that they have some information there. We're not necessarily going to read it together, but you can always feel free to go back and read through it. The next page talks about the fact that the exponential functions and logarithmic functions are inverses, because if you graph them, they are mirror image symmetric across the diagonal line y equals x. So a log, an exponential expression, or an exponential graph and a log graph would be inverses. And finally, they list all sorts of other properties of logarithms. We won't necessarily read through that together, but yeah, you can always go back and look at it. So let's start right here. These are some excellent warm-up questions for us to discuss and solve. In fact, I think that you can do all of these. Go ahead on your own. I'll get you started. Let's just remind ourselves how to tackle a problem like this. I'll do number 1 and number 5 just to get you started. It just says to rewrite the exponential as logarithmic and rewrite the logarithmic as exponential. This is your fundamental approach. If somebody hands you an exponential problem to do, they're assuming you're going to convert it to logarithmic. And if somebody hands you a logarithmic problem to do, they're assuming you're going to convert it to exponential. Now that might sound weird. If they want me to solve a logarithmic, then just give me logarithmic. Or if they want me to solve exponential, just give me exponential. But that's not normally how it goes. What you're normally presented with is a problem in exponential form, and to solve it, you have to convert to log form. And if you're given a log problem, you have to, in order to solve it, you have to convert it to exponential. Okay, so for number 1 then, you would have your problem 2 to 3 equals 8, and all I want you to do is just switch it into logarithmic form. So recall the first number stays the same, that becomes the base, log base 2. And remember, it's teeny tiny and down below. And then you switch the exponent and the answer, so it's log base 2 of 8 equals 3. So there's number 1. You can go ahead and do number 2, number 3, number 4. I'll just walk around to help. But then number 5, they're giving it to you in log form. And whenever you see the problem in log form, first of all, try to answer it. Say to yourself, 25 to the what is 5? Right? 25 to the what is 5? That one's a little bit of a mind bender. You might want to write it down. 25 to the what is 5? And by staring at it for a while, you might say, well, gosh, I don't really know because the number gets smaller. But I know that the square root of 25 is 5. And how do you rewrite the square root as an exponent? If I wanted to write square root of 25, I could write that as 25 to the what? Yeah, to the 1/2. So in fact, yes, this problem does make sense. It's 25 to the 1/2 equals 5. All right, so yeah. When you see a problem in logarithmic form, you rewrite it in exponential form. So again, the first number stays the first number, and then you switch these two. I always think that in my head is left to the right equals middle. So 25 to the 1/2 equals middle. And writing it down like that, is that a good final answer? Maybe not. Maybe what you'd really want to do is rewrite it as the square root of 25 equals 5. Because that way anybody walking down the street would look at it and say, oh yeah, sure, square root of 25 is 5. If you wrote it like this, that would be like, for someone you don't care much for as a friend, you're like 25 to the 1/2 equals 5. Ah, figure that out. No, just go ahead and rewrite it the normal way, which is root 25 equals 5. Okay, everybody go ahead and work your way through those problems. Let's walk around and answer any questions. You're just converting. The first one always stays. The first one is 1. And then it's the other two that switch, the -3 and 1. So you're right about the other. Yeah, 120, 1 over 125. And then it equals 2. So maybe you try the first number stays the same. Whatever you need to do to kind of remember. Yeah, I'm going to start by writing it as log base e of 1 equals 0. And then once you have log base e So then you could rewrite it as L. Yeah. Yeah, that's going to be 1. Yeah. No, what did we say about our calculator about this log and ln? If you see log without a number, that number is. What? Super. All right, super. Let's review what you got. I'll just call on some folks to give us the answers. What did you write down for number 2? Number 2, Erica, what did you write down for number 2? Yeah, perfect. Log base 5 of 1/125th is -3. And then for number 3, what did you get, Joseph? Yeah, perfect. Log base 4 of 32 equals 5/2. And for number 4, what did you get, Josh?
Number 4?
Yeah.
I got log E.
Yeah, log base E.
Log base E. The power of 1.
It's not to the power of 1. Remember, when you read it, it should sound like this. Log base 2 of 16.
Log base E of 1.
There you go, perfect. Log base E of 1 equals?
0.
Yeah, perfect. And then, folks, how could we rewrite this? How could we rewrite this in terms of what your calculator button would say? Log base E is really ln. So you write down ln 1 equals 0. And that would just be a little more simplified. Log base E of 1 equals 0 is perfect. But you can rewrite it in terms of your calculator. Okay, number 6. Let's see here. What did you get, Abe?
Log base 3 of -4 equals 1/81.
Well, we're going to convert it from log form to exponential form. So the log won't be there anymore. It'll just be an exponential. I think what you have written down there.
Okay, yeah.
Oh, okay.
3 to the power -4 equals 1.
Yeah, 3 to the power of -4 equals 1/81. And notice, folks, that it really does. Because what does a negative exponent tell you to do? Take the reciprocal, so that's really 1/3 to the 4th equals 1/81. And then 3 to the 4th, maybe you spent the weekend working on memorizing all those powers of 2, 3, 5, and 10. So 3 to the 4th would be 3, 9, 27, 81. So sure enough, 1/81 equals 1/81 is a true statement. Therefore, 3 to the -4 equals 1/81 is a true statement. Okay, and then number 7. Number 7, how do you rewrite that one? Silly? That's okay. What is log without a number? If you see log without a number, what is the number? Yeah, 10. So the first thing you can do is start by rewriting that as log base 10 of 100 equals 2. Now how do you convert that to exponential form? And again, you can always do left to the right equals middle. So Celine, what would it be? Left to the right equals middle. Yeah, exactly. And then that's, again, obviously true. 10 squared is 100, so you've got it. And then number 8, how can we rewrite number 8? So that says ln E equals 1. So first of all, how do we rewrite this? That's your calculator button. So how would I rewrite ln? How about Guadalupe? How would I rewrite ln? What's the definition of ln? Log base E. So it's really log base E of E equals 1. And then we want to convert this to exponential form. So left to the right equals middle, what would it be? Yeah, e to the 1 equals. Again, that's obviously true. E to the power of 1 is equal to e. Okay, so all of those nice direct problems in which you use the definition of log form and exponential form simply to rewrite it and to make the fact more obvious. Like for instance, just somebody walking up on the street, ln e equals 1 might not be a very obvious fact. But e to the power of 1 equals e is an obvious fact. So what we're doing is taking each of these problems and taking it from a not so obvious fact and turning it into a very obvious fact so that anyone could confirm that these are in fact true equations. Okay, this next set of problems, really fun. We're going to actually solve for the answer. Each of these, you'll notice, they're not equations. These are questions. Every single problem on there now is a question. Recall, just like this, before I wrote the 4 there, log base 2 of 16 is a question. It says 2 to the what is 16? 2 to the what is 16? So all of those are questions. Go ahead, everybody, start at the top, and go ahead and try to answer a few of those questions. You can use the first page of your log notes that we took last time to remind yourself of some of these facts, because we did do powers of 3 and 2. Go ahead and try to answer some of those off the top of your head as a question. Nice. And just a thought for you, like in terms of asking the question, like number 1, it's log base 3 of 27. You could do that in a couple of ways. You could say to yourself the question, 3 to the what is 27? So you could go ahead and write down 3 to the what equals 27. And maybe looking at that will spark your memory a little faster about, well, what power would I need that to be? And therefore, x equals 3, because 3 cubed is 27. Or alternately, you could write this as equals x. You could take any question and just say, well, I don't know what it equals. I'll just say it equals x. And then now you can convert it into exponential form. Left to the right equals middle, and you still end up writing down the exact same thing. You'll notice that however you view it, if you just view it as a question, 3 to the what is 27, you'd write down this. Whereas if you write equals x and then convert it to exponential form, you'd write 3 to the x equals 27. So you just want to choose one of those two frameworks of how you want to view each of these questions. Nice. Oh, I like when you're doing this. Actually writing down the questions. We don't have powers of 6 over here. So how do you do that? Oh, okay. Well, I'm just curious. It is not correct, but I was curious what you did to that. Nice. Take another 30 seconds and try to answer any more. At some point, they get a little tricky. mean, this is a question that says 36 to the what is the fourth root of 6. So you're going to try to answer the question, which will give the answer. Yeah, probably the last two rows, they're pretty tricky. And I'll role model for you some great solution strategies. Okay, let's try them together, folks. Let's review. So number 9, we had 3 to the what is 27. So 3 to the what is 27. Isaac, what'd you get? 3 to the what is 27. For number 9.
X equals 3.
Yeah, this one is 3 to the what is 27, and that's a question, and so the answer is x equals 3. Okay, how about number 10? In number 10, we had 2 to the what is 32. So what did you get for that one, Jessica?
5.
Yeah, 2 to the 5. So x equals 5. Now, keep in mind here that the way I've written this down, I convert it to exponential form, and then it actually says what x was. But the alternative way of doing this would be just to keep it the way it is, log base 3 of 27, and then you would just say equals 3. Or if I had the original expression here, log base 2 of 32, you would just say it equals 5. Because literally this expression right here is equal to 5. And literally this expression right here is equal to 3. So simply writing an equal sign and the number after it is perfectly acceptable. You don't have to rewrite it as x equals. Okay, how about number 11? Number 11 says 6 to the what is 1/36. Who'd like to volunteer and answer for that one? Jackie? Yeah, it is -2. Now, very curious, Jackie, how did you get that? 6 squared is 36. And that's just the reciprocal, so it'd be negative. Now, notice, folks, by having this sheet in front of you, you now know how to create a table for any base. So for instance, if you wanted to, you could go ahead and say, well, 6 is my base, so I'm going to go ahead and write down 6 to the 1 is 6, and so 6 squared is 36, and so 6 cubed is 216. And then you can start going backwards and say 6 to the 0 is 1, and then 6 to the -1 is 1/6, and 6 to the -2 is 1/36, and 6 to the -3 is 1/216. So does that table look exactly like what we did on the first page? Yeah, so you can do that for any number. You know, you can do that for a base of 7, or 9, or 8, or 11, or 13. You know, you can just really quickly bust out your own table to help you think through a problem like this. Or as Jackie did, she knew that 1/36, watch this, she knew that 1/36, I'm just going to go over here, that 1/36 is really 1/6 squared, which you can rewrite as 6 to the -2. And therefore, 6 to the what is 6 to the -2? Now really take a look at that. 6 to the what is equal to 6 to the -2? What must x be? If the left side and the right side are truly equal, and this right side says 6 to the -2, then x must be -2. It just has to be by the sheer logical force of the fact that we want the left and right hand side to be the same. Okay, so how about number 12? That one said log base 8 of 4. Log base 8 of 4. Did anyone answer this one?
2/3, right?
Yeah, I do believe it is 2/3. Let's take a look at it, folks. So this would be 8 to the what is 4, and Victor's saying that it's 8 to the 2/3. Now, Victor, I'm curious, how did you get that?
I started punching.
Oh, wonderful. Victor just started punching in numbers. And you actually punched in 2/3 of all possible things. What else did you punch in?
Half.
Half, and then just other fractions? You just kind of figured it would be a fraction. Okay, very nice. Anybody else? How did you get your answer of 2/3? Okay, absolutely. Everyone write this down with me. We're about to explore a problem-solving strategy that is related to logarithms, and we're going to do this strategy over and over. So everybody start by writing down log base 8 of 4 equals x. Right? And let me emphasize that a little more. In mathematics, if you're presented with an expression and you have no idea what it equals, and you're completely ignorant, and you're like, oh my gosh, I have no idea. What is that thing equal to? I don't know. So what you do is you say, I don't know what this is, but let it equal x. Okay, it's a perfectly valid problem-solving strategy. You're saying, I don't know what this thing is, so I'm going to give it a name. I'm going to call it x. And by creating an equation, I now have something I can manipulate. Like without that equals x, it's just an expression, and I can do nothing. But if I write equals x, now I have an equation, and I convert it into exponential form. So now everybody convert this into exponential form. 8 to the x equals 4. Now, we're going to use a strategy called make both sides the same base. We want both sides to be the same base. Now, hopefully you recognize the number 8 and 4. Looking at the numbers 8 and 4, I hope you recognize them if you think about the first page of your sheet. What do you know about the number 8 and the number 4? Number 8 and number 4 are both? Yeah, they're both powers of 2. Right? They're both powers of 2. So we could go ahead and rewrite 8 and 4 as powers of 2. So 8 is really what? 2 to the power of? 8 is really 2 to the power of 3. So I write 2 to the power of 3 to the power of x. And over here, 4 is really 2 to the power of 2. So that's really 2 squared. Now again, everybody needs to be writing this down. This is part of our sample problems that we're doing here. So 8 to the x equals 4 is really 2 cubed to the x and 2 squared. Now, what do our exponent rules say? When you have a number to an exponent, what do you do with the exponents? Let's just review that rule real quick. If you have, here's all of our exponent rules. If you have, let's see here. X to the a times x to the b, then what is that really? X to the a plus b. And then if you have x to the a divided by x to the b, what is that? A minus b. So if you're multiplying the bases, then it's addition. If you divide the bases, it's subtraction. And what if you have x to the power of a to the power of b? What's our rule? That becomes x to the a times b. All right? This is probably worth writing down because dealing with logarithms, we're really dealing with exponential expressions quite a bit. So you'd want to be able to remember and use these rules at any time. So this is the product, quotient, and power rule for exponents. So when you raise a power to a power, you multiply the powers. So what do we have here now? This is really 2 to the power of 3x equals 2 to the power of 2. Now look what we've done here. This is very important. We took our log expression, which we didn't know, and we said, I don't know what that is, so I'll set it equal to x. That way I have an equation that I can manipulate, an equation that I convert from log form to exponential form. Once I had exponential form, it was up to you to just realize and say, oh, 8 and 4, I recognize those numbers. Those are both powers of 2. I can rewrite both sides as a power of 2. So you did that, and now, using that exponent rule, we now say 2 to the 3x equals 2 to the 2. Now, what do we know then? If these two sides are really equal to each other, and the bases are the same, that's really important, since the bases are the same, if this exponent is a 2, what must this equal? What must the 3x equal? It must also equal 2. If I want the right-hand side to be equal to the left-hand side, they both had better be 2 to the power of 2. So what we know now is if the bases are the same, the exponents have to be the same. And by logical force, I can now say 3x must equal 2. Okay, that's a bit of a logical jump there. Once you have both sides written as the same base, then whatever the exponents are, they must be the same. If we're saying that this equation is true, the exponents must be the same. So now I have 3x equals 2, and it's a simple matter of solving that equation. 3x equals 2 is a very basic, just simple equation. So x is being multiplied by 3, I divide by 3, and I get x equals 2/3. Which you'll recognize was Victor's guess that he figured out. It's 2/3. And then, of course, you should type that in your calculator and verify. You can just take your calculator and type in 8 caret parenthesis 2 divided by 3 and see if you get 4. Maybe better. Everybody try typing that into your calculator real quick. 8 caret parenthesis 2 divided by 3. Very important that you use those parentheses. You can't just type 8 caret 2 divided by 3. At least I don't think you can. 8 caret 2 divided by 3. No, that would be incorrect. It has to be 8 caret parenthesis 2 divided by 3. And if you do that, it really does equal 4. Okay, folks, we're going to use this technique quite a bit, where the technique, you rewrite both bases as the same side, or as the same base. So rewrite both sides of the equation with the same base. And what you draw from that is if the bases are equal, then the exponents must be equal. As well. So that's our first big strategy of solving some logarithmic expressions. So let's try that again. We're going to go ahead and try number 13. That was part of my previous solution there. So here's number 13. And in number 13, we have log, that is our next one, right? Yeah. Log base 1/5 of 625. Now, I'd like you just to let your eyes rest on that expression for a moment. Just look at the numbers 1/5 and the number 625. What do they have in common? Yeah, they're both powers of 5. They're both powers of 5, right? So 625 is what? 5 to the, you can look at the first page of your sheet. Yeah, that's 5 to the 4th. And 1/5 is really, yeah, 5 to the -1. So you can look that up on the first page of your packet. So that's really 5 to the -1, and that's really 5 to the 4th. Okay, so again, it's very valuable to be able to just look at numbers and say, hey, those are both powers of 5. Okay, so what's our strategy? We say, I'd like to know what log base 1/5 of 625 is. In other words, 1/5 to the what is 625? You look at it, you say, hey, I have no idea what that is, so you set it equal to x. That's always a great strategy. If you're given an expression, you don't know what it's equal, say equals x. That way you have an equation that you can manipulate. And now, as I said, if you're given a logarithmic equation, switch it to exponential equation. So now this is really going to be 1/5 to the x equals 625. So where do we go from here? There's a couple thoughts. One is immediately go ahead and rewrite 625 as a power of 5. So what is it again? 5 to the power of 4. Now, you have two different options right now, and I'd like you to feel comfortable with both. On the one hand, we need the bases to be the same, right? That's our strategy. Rewrite both sides of the equation with the same base. Right now, this base is 1/5. 1/5 to the x. This base is 5. So the bases are not the same yet, but they're so similar to each other. So how do I rewrite the bases to be the same? We could write both of these bases as 1/5. And I can easily change 5 to a 1/5 by using a negative exponent. Or I can rewrite 1/5 as 5, again by using a negative exponent. So let's just see how that works real quick. If I have the number 1/5, that's really 5 to the -1. Does everyone feel okay with that? It's an important definition. That you can just take any fraction you want and flip it and put a negative exponent on it. Alternately, I can take my number 5 and rewrite that as 1/5 to the -1. Oh, sorry. It can either be 1/5 to the -1 with a -1 on the 5, or it could be 1/5 to the -1. All right, so all of that so far is the same. Generally speaking, what you can say is that if you have a fraction, a over b, and this is really exciting, okay? Maybe no one has ever told you you're allowed to do this. If you have the fraction a over b, you can just go ahead and change it to b over a and just write it as to the power of -1. You have the freedom to do that anytime you want to. You can just take a fraction, take the reciprocal, and just put a power of -1 on it. And you're allowed to do that anytime at all. So what are we going to do then? I think I'll go ahead and change 1/5 into a base of 5, because I would prefer to have whole number bases. So I'm going to change 1/5 into 5 to the -1 to the x equals 5 to the 4. That's a little sloppy. There. Did everyone do that? I just changed 1/5 into 5 to the -1. Now again, our exponent rule says that if you raise an exponent to an exponent, you just multiply the exponents. So now I have 5 to the -1x equals 5 to the 4. And then as far as like a little mantra to say in your head, so that you're talking to yourself in English, you'd say, if the bases are the same, the exponents must be the same. So if you verify that the bases are the same number, then the exponents must be the same. And so now we say -1x equals 4. And look at this huge jump that we just did there. We took an exponential equation and changed it to just a normal, regular, simple, run-of-the-mill algebra problem. We're not saying that the 5's canceled out. They didn't. What we're saying is that by sheer force of logic, if you have an equation and the base on both sides is the same, then the exponent on both sides must be the same. And so you equate the exponents. And so we divide off the -1, and we get x equals -4. Now we just did a whole lot of work. How can we check our answer? How do we check that -4 really is the answer? We'll plug it into what? Yeah. We would plug it into this thing. Because we don't know how to solve this on our calculator. So we can't actually confirm that on our calculator, but we can confirm this on our calculator. So everybody go ahead and type that into your calculator. Type in parenthesis 1 divided by 5, parenthesis, caret, parenthesis, -4, and see what it equals. Type all that into your calculator. You have to use all those parentheses. So parenthesis 1 divided by 5, parenthesis, caret, parenthesis, -4, parenthesis, and what do you get? Should be 625. Oh, I don't want to erase anything. That's also good. I think I'll do this. All right, there we go. Folks, questions before we keep going? I hope you all wrote this down. That our strategy that we're using for the rest of this page is to rewrite both sides of the equation to have the same base. And if the bases are equal, the exponents must be equal. That's our strategy. So let's take a look at the next one. Oh, delightful. Number 14. It says log 0.01. Now, first of all, how can we answer this question right now, really quickly? You can just plug it into your calculator, folks. Everybody do it. Type in log 0.01. You can just type it right in, log 0.01. It's always a good idea to put parentheses, but if you type log parenthesis 0.01, what do you get? Just get -2. So you can say, hey, wonderful, Mr. G, we're done. Let's move on. But no, let's not move on. Let's really look at this one and see how to solve it. So first of all, log of 0.01. What base is that? Yeah, it's not written, and if it's not written, it's a 10. So now what we have is log base 10 of 0.01. And so we're staring at this expression, and we say, I don't know what it is. So what do you do when you don't know what an expression equals? You set it equal to x. And by setting it equal to x, you now have an equation you can manipulate, and you can convert this log equation into an exponential equation. So now we convert. We say left to the right equals middle. We have 10 to the x equals 0.01. Now again, our strategy is make the base number of both sides the same. Right now, this is a base of 10, and this is 0.01. How do I rewrite 0.01 as a power of 10? You can look again at the front side of your notes that you took from the first day, but how do you rewrite 0.01 as a power of 10? There are a few options. So 0.01, first of all, did you write it down on the first page? Now 0.01 was, on your first page, we wrote down 10 to the -2, right? Because you moved the decimal twice to the left. So it's 10 to the -2, but also, just look at the place value. The place value of the decimal system, that's the 10th place, and that's the 100th place. And therefore, this is literally 100th. So you can do it either way. You can rewrite it as 10 to the -2 directly, or you can rewrite it as 1/100th. I'm going to do it as 1/100th, 1/100th, just so you can see the process. So this is 10 to the x, this is 1/100th. And again, I want to rewrite this as a power of 10. So at this point now, you probably see that you can write it as 1/10 squared. That's one option. You can rewrite 1/100 as 10 squared, 1/10 squared. And then you can simply push that 10 into the numerator. You're allowed to. And change the +2 into a -2. So now that's really 10 to the -2. Now you notice 10 to the -2 was one of your options. You could have just written that originally. But I want to show you how to manipulate things. You could use 0.01, use the place value system and say that's 1/100th, change that to 1/10 squared, and then push the 10 into the numerator as 10 to the -2. And now here, again, our strategy says if the bases are the same, then the exponents must be the same. And therefore, x equals -2. And you might say, Mr. Zhu, my goodness, we knew that. We already did that on our calculator. So why did we do this? Because the goal is to be able to figure these things out without your calculator. It's like the first couple units we did in here. We're gonna learn all the steps and all the work so that you can make a graph, even though you are allowed to look at the graph and calculator and see what it looks like. Okay, so that's number 14. Let's try, okay. Yeah, okay, everything's great. Let's try number 15. Number 15 says ln e. What would you do with that? Okay, just looking at that, it looks pretty strange, pretty mysterious. What would we do? That's right. That's right. And maybe the first thing we'd do is, well, first of all, can you type that into your calculator? Yeah, ln is actually a button on your calculator, everybody. Go ahead and just rewrite that as ln parenthesis e caret 3. Let's see what you get. Type it in your calculator. So that's going to be ln parenthesis e caret 3. And remember, you get the e button it's right above the ln button. So you have to hit second ln, and that calls up the e to that function. So go ahead and type in ln e to the third, and you get. Great. So again, this particular one you can just solve on your calculator. Well, let's see how we would do it. We would say ln of e cubed, and you're looking at it, and you just admit your ignorance, and you say, I have no idea what that is, so I'll set it equal to x. So furthermore, you'd have to rewrite ln by the definition, which is log base e. So now we have log base e of e cubed equals x. Okay, so this was one strategy. Use your calculator. We're now looking at a new strategy of solving it by hand. Okay, so now that we have log base e of e cubed equals x, what do we do? Yeah, we just convert it to exponential form. That's always a good strategy. Take your log form, convert it to exponential form. Take your exponential form, convert it to log form. So left to the right equals middle. We have e to x equals e to 3. And therefore, by the sheer force of logic, if the two bases are the same, then the exponents must be equal, and therefore x equals 3. All right, let's try another one of those. Log base 6 of 1. So number 16. Log base 6 of 1. We're going to go and try that. Implement this strategy that we're talking about. That when you're given an expression, you don't know what it is, you admit your ignorance, you say, I don't know what that is, so you set it equal to, and then, since it's in logarithmic form, you convert it to, very nice. So you say, I don't know what that is. I'll set it equal to x. I rewrite it. That's 6 to the x equals 1. And then we want the same base. How do we rewrite this as the same base? This is obviously a base of 6. How do I rewrite 1 as a base of 6? Well, that would be a fraction. That's true. 6 over 6 would be equal to 1. We want to rewrite it as a power. 6 to the power of what equals 1? Yeah, 6 to the power of 0. And now this is another time where it'd be helpful to have that sheet in front of you, or what I already wrote on the board and then I erased it, was the powers of 6. So 6 to the 1 is 6, 6 to the 2 is 36, I can keep going, and then 6 to the 0 is 1, and then 6 to the negative 1 is 1/6, and 6 to the negative 2 is 1/36. So in general, something that we don't want to memorize is that you can always rewrite the number 1 as any power you like to the power of 0. Notice how weird that makes the number 1. Right? Because number 1, I can rewrite as 2/2, or 1/1, or 3/3, or 47/47, right? So I can already rewrite the number 1 as any fraction I want. But now I can also rewrite it as any number to the power of 0. 5 to the power of 0, 11 to the power of 0, 13 to the power of 0, 172 to the power of 0. Right? Like 1 is a pretty interesting number because it can be written in infinitely many different ways, either as a fraction over itself or as any number to the power of 0. However, just PS, folks, and you can all go investigate this. What's 0 to the power of 0? We say anything to the power of 0 is equal to 1. What's 0 to the power of 0? Type it into your calculator and see what you get. It's the one exception to the rule of anything to the power of 0 is equal to 1. So in any case here, we have same base, therefore the exponents must be equal, and therefore x equals 0. What was 0 to the 0? Yeah, it's a domain error, it's undefined. Maybe later today you'll play around with that and think about why it's undefined. Like, why is anything else to the power of 0 equal to 1, but 0 equal to 0 is not? Because, for instance, you can even take a negative number to the power of 0, and it still equals 1. You can take a fraction to the power of 0, and it still equals 1. You can take pi to the power of 0, and it still equals 1. But of all things in the universe, just 0 is the only thing that you can't let be the base of the power of 0. It won't equal 1. It'll be undefined. That's a little mystery for you to go think about. All right, number 17. That's log base 36 of the 4th root of 36. Log base 36 of the 4th root of 36. Whew, this is a good problem. Now, I've written up a bunch of exponent rules here. There's one more that we need to remind ourselves of, and that's how to rewrite a root. So if you have, you'll all recall that the square root of x is equal to 1/2. And I'm sorry, square root of x is equal to x to the 1/2. And the cube root of x is equal to x to the 1/3. And in general, any nth root of x is equal to x to the 1/n. So there's another definition you need to have at the ready. These are a lot of definitions you need to have at the ready, huh? This is what makes math tricky, is that you just need to have all these definitions floating around in the back of your mind. Like, oh yeah, sure, I remember all these definitions and I can use them at a moment's notice. It's a lot of definitions to keep in mind. Okay, so what do we do with this thing? Well, that's certainly true. You could immediately, if you wanted to, since the 4th root of 36, you could just rewrite that as log base 36 of 36 to the 1/4. You can do that first. Now we're still wondering, what is this thing equal to? So what's our first strategy? Yeah, set it equal to x. Admit you're ignorant and say, I don't know what that thing is, I'll call it x. So now we can just convert to exponential form. So left to the right equals middle. 36 to the x equals 36 to 1/4. And I hope that now this is feeling routine. That you take an expression, you set it equal to x, you convert it to exponential form, and if the bases are already equal, then the exponents must be equal. So here we see immediately that x is really equal to 1/4. And if you had a way to type that into your calculator, it would equal 1/4. How does everybody feel about this? Any particular questions you'd like to ask? Well, let's see here. There's still a few more problems to do. I'd like us to finish them before I move on. One thing that's so particularly exciting, I might have to sell you on this. Well, like, look at a problem like 7 to the power of log base 3 of 3. Like, look at that thing. 7 to the power of log base 3 of 3. It is log base 7? Oh boy, I cannot even see that. That makes more sense though. Well, I mean, either way, it'd be fine. Is it really log base 7?
Yeah.
Okay. We'd be able to solve it at log base 3 as well. 7 log base 3. Okay. So here's what's exciting about mathematics, and it's just a metaphor for life. All right. You look at this expression, and maybe the first thing that goes to your mind is, I don't know. Right? I don't know. I have no idea. I've never seen anything like this before. It looks totally alien. This is crazy town, right? And that's what a lot of personal problems are too. You wake up in the morning, your car doesn't start. You wake up and your coffee maker doesn't work. You wake up and who knows what. It's a mystery and you're like, oh, I don't know, right? So what do when confronted with a situation like that? What's our new strategy? Do what? Yeah, set it equal to x. This is like a whole new strategy in math, that if you have some expression, you don't know what it is, your very first strategy is to just admit ignorance and set it equal to x. Say, I don't know what that thing is, so I'm going to call it unknown. But now it's an equation, and now I can manipulate it. So now what do we have? Is this a logarithmic expression or an exponential expression? This is tricky. Is it in exponential form or is it in log form? Who thinks exponential form? You do? Who thinks logarithmic form? And this is really tricky because like you're staring at the word log. So there's probably part of you that's like, this has to be in log form. I mean, if this is in log form, I don't know what it is. But the fact is, it's exponential form because you have a base to an exponent. And I don't care what the exponent is, if you have a base to an exponent, it's exponential form. So we have an exponential form, so we want to convert this to log form. So we're going to drop it straight down and convert to log form. So this would be the first number stays the same. So that's log base 7. And then recall that these two sides switch. So this is log base 7 of x equals log base 7 of 3. And what's that, Josh? Yeah, it's a little crazy. Now notice, we're in the same situation as before. Previously, we were saying that if the base is the same, then the exponents must be the same. That's what we said. If the base is the same, the exponents must be the same. So if the bases are equal, the exponents are equal. Now what we're saying is, if the log type is the same, then the argument must be the same. So since they're both log base 7s, then whatever's inside of them is called the argument. Therefore, x must be equal to 3. It's by sheer logical force. Now you might go back to the original feeling of like, 7 to the power of log base 7 of 3, I don't know what that is. That's super crazy. And now we're saying the answer is 3. That might not bring any satisfaction. Like, okay, well, the answer is 3. It still looks pretty crazy to me. And that's true. It still looks pretty crazy, but the answer is 3. As a bonus question, look at this one. As a bonus, what would the answer to this one be? Could we do the same thing? Could we just admit ignorance and set it equal to x and then convert? Could. We very well could. Well, let's try that. If I set it equal to x and convert, that'd be log base 7 of x equals log base 3 of 3. Can we use the same strategy we just said? Is the log type the same? No. Okay, so we can't just use that same strategy. The log type is not the same. However, is there some part of this that we can figure out? We know what 7 is. 7 is 7. What's log base 3 of 3? Like, let's just take a moment and say, I wonder what that is. Okay? This is a specialization of admitting our ignorance. Right? So we're saying 7 to the log base 3 of 3, I have no idea what that whole thing is. Well, let's just focus on this part right here. What's log base 3 of 3? So if you write down log base 3 of 3 and say, I wonder what that is. I don't know. But then that's 3 to the x equals 3. And therefore, what's x? It's going to be 1. And therefore, log base 3 of 3 is equal to 1, so 7 to the power of 1 is just 7. That technique was very different from this technique. And yet it all started in admitting our ignorance. Right? And saying, okay, just choose something to say what is it, and setting it equal to x. Okay. One more. Let's do the last two and then we'll take a break. Number 19. That's log base 36 of 36 to the 260. Oh, there we go. So we're kind of talking about two different things right now, folks. We're talking about learning logarithms and the vocabulary and the rules that go with logarithms, such as all these exponential rules and taking powers. But we're also talking about a way to deal with ignorance. And ignorance sounds like such a terrible word, like you're ignorant. That's an insult. Ignorance just means you don't know. You could also call it, well, no, it's not about agnosticism. You're just saying I don't know. What would you call that other than ignorance if you wanted to make it sound better? What? What'd you say? Yeah, I mean, ignorant is fine. You can just say, I don't know currently. Like, I currently don't know. Okay, so, again, we say, I don't know. I set it equal to x. It's in log form. I convert it to exponential form. That's left to the right equals middle. So 36 to the x equals 36 to the 216. And since the bases are the same, the exponents must be the same. And so x equals 216. Okay, there. We've done this strategy now many, many times. I hope that now this one looked really simple. Like, well, this is just easy, right? I mean, we just set it equal to x and rewrite it, and then the answer is just there. So maybe this last one will be a little tricky. Whew, it will be. ln of 1 over the square root of e. So what is that thing? First of all, can we get the answer right now? Like really quick, how can we get that answer? You just type it in your calculator. We can all do this one. In your calculator, go ahead and type ln parenthesis 1 divided by square root of e. And since e only comes up as e to the power of, it's really the square root of e to the power of 1. There. So type that in your calculator and see what you get. ln 1 divided by the square root of e to the 1. If you type it in your calculator correctly with all those parentheses, let's see, ln parenthesis 1 divided by square root parenthesis e to the 1 parenthesis. Yeah, what did you get? Yeah, negative 0.5, which really decimals, it's actually more convenient if we think of negative a half, because we didn't memorize powers of x as 0.5, we do it as 1/2. When we think of a square root, that's x to the 1/2. I mean, I suppose you could memorize that as x to the 0.5, but I don't know too many people who do that. Whenever you convert a root, like the square root of x is x to the 1/2, the cube root of x is x to the 1/3. Nobody writes it down as x to the power of 0.3 repeating. That's a little weird. So in this case, even though your calculator said negative 0.5, we really want to write it as negative 1/2. Because it's evocative of this idea of exponents being fractions. Okay, so folks, let's try it. How do we actually get that answer without our calculator? Let me start by writing it down. So we would all start the same way. We'd say, ln of 1 over root e? I don't know. I don't know what that is. Now, there's a lot to rewrite here. No, this is another very important idea. In mathematics, we spend a lot of times rewriting things using definitions. So what's the definition of ln? Log base e. What's the definition of square root? To the power of 1/2. Okay, that right there is a massively important idea in mathematics. Is that if you're given something and you don't know what it is, rewrite it in a different way using the definition you know. So I'm going to do that one step at a time. ln is really log base e. Okay, that's the application of one definition. Baby steps, right? You just do one thing at a time. Now the square root of e. I'm going to rewrite that now as log base e of 1 over e to the 1/2. Then what? What would we really like to do here with 1 over e to the 1/2? Yeah, it'd be really nice if this wasn't a fraction. But specifically what this is a reciprocal. I'd like to push the e to the 1/2 up into the numerator. And you can always push anything from denominator to numerator or numerator to denominator by changing the sign on the exponent. So instead of 1 over e to the 1/2, that's really log base e of e to the negative 1/2. Right? So we just push our denominator into the numerator and change the positive 1/2 to negative 1/2. Okay, now what? We have a really nice, clean expression. And now this is log form. We convert to exponential form. So we say left to the right equals middle. E to the x equals e to the negative 1/2. And by sheer logical force, since the bases are the same, the exponents must be the same. And therefore, x is equal to negative 1/2. I wonder if there's a part of you that's looking at all this and saying, oh man, I mean, this is just so much trickery. Like a magician, when you know how they do their trick, you're like, that's not right. You know, they pull a coin out of your ear and then you realize they were holding the coin the whole time. You're like, well, that's not very impressive. I don't know if that's how you feel. Or if you're just like, oh man, there's a lot of steps. Well, we have a lot of feelings. All right. Well, we've done some really good work here, folks. We've looked at how to rewrite and solve exponential and logarithmic expressions with and without using our calculator. So next, we're going to talk about domain. Very exciting. We'll do some domain problems. We'll make a couple graphs. And then we'll move on to properties of logs. That sounded real good. And then, oh yeah, the change of base formula, solving regular exponential equations. Oh, it's so exciting. Some log equations. Oh boy. And then some applications. Okay. Yeah, we're moving right along. Let's take our break. Time is 9:07. Let's be back at 9:17. Yeah.
Oh, I'll do the Charlotte's class.
All right, folks, let's keep going. Now, everything we've done so far has all just been a matter of definition, right? You use a definition, you apply the definition, you transform the equation into a new equation, and you just keep on manipulating it until it turns it into a problem that you know how to solve. And so that's converting from exponential to logarithmic. That's applying all those exponent rules, like the product, the quotient, the power, knowing that the square root is really x to the 1/2, the cube root is really x to the 1/3. I mean, my goodness, there's just so many definitions to know and then to apply them. One question that might be in the back of your mind is, how do I know which definitions to apply? And how do I know what order to apply them in? Right? That'd be a very valid question. How do I know which definitions to apply? Where should I start? What should I do next? And to that extent, I have an unsatisfying answer to you. And that is, sometimes it feels like an amateur approach to a Rubik's Cube. And if somebody gave you a Rubik's Cube, what would your amateur approach be? You just start twisting it around until maybe you get to the answer, right? Or maybe, do you know those puzzles where it's like, I think it's called a 15 puzzle, where you have the numbers 1 through 15, and they're out of order, and you have to slide them up, down, left, right, until you get it all in position. I mean, there is a certain element of problem solving that is, you know, you try things. You try things and you try things until the answer falls out, right? That's problem solving regarding things that break around the house, too. You know, your vacuum breaks, so you just start fiddling with it, you know, taking things apart until you figure it out. So, well, it would be nice to always be able to say that mathematical problem solving is always like this straightforward process. Sometimes you just fiddle around with things until you figure it out. And that's the way it goes sometimes. All right, so we're taking a look at the domain now. Let's go ahead and remind ourselves, what's the domain exclusion for a logarithm? First of all, everybody go ahead and write down log parenthesis argument. Okay, so the word is argument. That's the word that's often used. You might say, well, geez, that's kind of weird. I mean, why don't they just call it input, right? It's the input into the log. Now keep in mind, the argument is the number that's going into the log, not the base. Okay, the base is not the argument. The base is the base. The base tells you what type of equation you're solving, like 10 to the what equals the argument. So just to kind of remind ourselves, in this particular problem, we're saying 10 to the what is equal to some positive number. That's the argument, the positive number that you're trying to equal. So when we said like 10 to the what is equal to 50, 50 is the argument. It's what we're trying to figure out how to rewrite as a power of 10. And so what we're saying now in terms of domain is that for a logarithm, the argument, which I suppose we can just write arg. Is someone okay with that? We can just write arg for short. Sounds kind of like what a pirate would say, arg. So argument must be strictly greater than 0. That's our domain test. Because remember, and you might want to remind yourself, you cannot log a 0 because that's undefined. And you cannot log a negative because that's imaginary. So our domain test is always going to be argument is greater than 0. Why is that? Because recall, when you have an exponential graph is always like that. And what that means is your graph is always in the top half of the plane. It's above the x-axis. The y value is always positive. That's an asymptote over there to the left. And the asymptote never touches the x-axis. So any exponential equation is always going to be a positive number. It will never equal 0 because the asymptote doesn't touch the x-axis. And it never dips down below the x-axis. Okay. So let's take a look at the first one, number 21. We're saying the function is f of x equals natural log of x squared plus 1. Now, before we do that, you know, what I like to do is just go on over here and graph it. So natural log of x squared plus 1. Now, recall, visually, how do you do a domain problem? Domain is how far you go left to right. So just taking a look at it, how far does this graph go left to right? Yeah, negative infinity to infinity. Is there a point right there? I wonder. Yep, there is a point right there. So it looks like the domain is all real numbers, that I can plug any number I wanted in there, right? So just looking at the graph, it appears we have our answer. that for the problem natural log x squared plus 1, it appears as though the domain is negative infinity to infinity. Now that was just solving the problem graphically. You're allowed to solve problems graphically. It's not against the rules, not illegal, it's not immoral. But how do we actually do it? Algebraically, you take the argument and say x squared plus 1 and solve it for greater than 0. So when is x squared plus 1 greater than 0? This is an interesting one. So you would go about solving for x, right? You'd say, well, I'm going to subtract 1 from both sides, and now we say, when is x squared greater than negative 1? Right, and right there, we can solve this problem by inspection in a couple ways. Remember, what happens anytime you square a number? A positive times positive is positive, and a negative times a negative is positive. So this thing is always going to be positive. And is a positive number bigger than negative 1? Yeah. The only exception is if you plug in 0. What's 0 squared? 0. And is 0 bigger than negative 1? Yeah. So we just showed that this thing will always be true if you plug in a positive number, a negative number, or 0, which is everything. So this thing is always true. Or if you wanted to, so that's just solving by inspection. That's called solve by inspection. Solving by inspection is a very technical word that means you think about it. Right? That sounds like a silly approach. Solve by inspection. You think about it. You think about all the different cases. The other thing you could do is actually just graph that. So when is x squared greater than negative 1? Or better yet, when is x squared greater than 1? We learned that anytime it's greater than 0, what are you asking about the graph? X squared plus 1 looks like this. And when we say greater than 0, what are we asking about the graph? We're saying, when is the graph above the x-axis? When is this graph above the x-axis?
Always.
Always. So that's a few different ways that you can solve this problem. 3 different ways to solve the problem total. One is by inspection, knowing that anytime you square anything, it's 0 or positive, so that's always true. Graphing it and saying, when is the graph above the x-axis? That's always true. Or graphing the original problem and just looking at it and seeing how far it goes left to right. Okay. You know, folks, a lot of times I show you more than one way to solve a problem. And I have to admit that one of my motivations is just to show you multiple ways so that you can choose the way that works best for you. And I could say that that's why I show you multiple ways, because I want you to have options. You're like, oh, I like that way, I'm going to solve it that way. But do you know my real goal in showing you more than one way to solve a problem? That you would do all of them. That's a really good idea. Like if you have more than one way to solve a problem, do them every way. Because that way you should see that every approach you use leads to the same answer, and it builds your confidence that your answer is correct. Okay, let's take a look at this next one. We have a function, and it's log base 7 of 4x plus 8. And we'd like to know what numbers can I plug into that. Now, first of all, it's base 7. Does that matter? Maybe. In this particular case, it really doesn't. Right, whatever that base is, that could have been a 10, it could have been an e, it could have been a pi, it could have been a 3. It really doesn't matter what the base is, because what we're really saying is the argument has to be, just has to be greater than 0. So that's all that really matters. The base doesn't really matter, just the argument has to be greater than 0. So let's solve this one the traditional algebraic way. We're just saying 4x plus 8 has to be greater than 0. And therefore, subtract 8 over 4x has to be greater than negative 8. Find 4 over, and therefore x has to be greater than negative 2. All right, so this is just a normal, straightforward algebraic solution of a domain problem. We're saying the argument must be greater than 0, so x must be greater than 2. What does that look like on a number line? What are we saying about our domain? Here's negative 2, and it has to be strictly greater than it. So positive infinity. And so what would our domain notation say? Or interval notation? Yeah, negative 2 to infinity. And that would be our answer. Notice how you kind of flow through different thinking modalities. The first thing you say is you set the argument greater than 0 and you do algebra. The next thing you do is you plot that algebraic solution as a number line so you can see it. And then you take the number line and you convert it into interval notation. Right? That's a flow of thinking. Now, how can we check our answer? we can go ahead and just graph log base 7. Now, as I said, log base 7, this graphing calculator will not do base 7. So the best I could do is just do log of 4x plus 8. I can't actually capture the base 7 aspect. But it really doesn't matter if it's base 7 or base anything, because the graph is still going to, you can still just inspect it. And so how far does this graph go to the left? To -2. And it goes to the right to infinity. So it really doesn't matter what base it was. The domain is still going to be from -2 to infinity either way. Okay, let's try another one. Number 23. We have f of x is the log of x squared plus 9x plus 18. So again, you could approach this any way you like. We could just immediately graph it. You can just immediately graph it. You know, there's absolutely nothing wrong with just immediately graphing a problem so that you can just visually see what the domain is going to be. Ooh, kind of interesting. What does this mean? First of all, how far to the left does it go? We assume to -infinity. How far to the right? To infinity. Now, what's happening here in the middle? It looks like there's a gap. And where does that gap exist? It looks like the gap exists between -6 and -3. It looks like those are two vertical asymptotes, doesn't it? So we're saying that the graph does exist from -infinity, then it stops at -6, jumps over, starts again at -3, and continues on to the right. So just by looking at our graph here, we could go ahead and write down what we believe our answer to be, which is what? I'm going to make a number line first. It went from, what was it, -6 and -3? It was like that, to -infinity, and like that, positive infinity. Okay, so therefore our domain would be -infinity to -6, union, -3. Did I do that right? Okay. Okay, so that's just a direct graphical approach. But now notice, how do we apply the formal definition that the argument has to be greater than 0? So we take our argument and we say, I want x squared plus 9x plus 18 to be greater than 0. And so what does that mean graphically? I want this graph to be where? Which means above the x-axis. So I want to be above the x-axis, right? This is really, really helpful definition. We just think of above the x-axis or below the x-axis. Okay, so now what does that graph look like? Well, I would need to, can we factor that? Does this factor? What multiplies to make 18 to add to make 9? Yeah, 6 and 3, we can factor it. So that's x plus 6, x plus 3. What if we couldn't have factored it? What would we have had to do? Quadratic formula. Okay, so now I know that for this graph, I should have two x-intercepts, one at -3 and one at -6. So I've got -6, I've got -3, that's my x-axis, and therefore my parabola looks like that. Right? Notice what an interesting problem this is. What kind of function are we actually talking about? A logarithm function. And yet what graph are we analyzing right now? A parabola. Because the parabola is the argument, and the argument has to be greater than 0, which means it has to be above the x-axis. And therefore, where is the parabola above the x-axis? From, wait, and strictly above, not equal to. So from -6 to the left, and from 3 to the right. And therefore, we arrive at the same answer, that we would need to be left of -6 or right of -3. And that's the same answer that we got. So again, I showed you two strategies for this problem. On the one hand, I'm saying, hey, now you have two different strategies. You can try it either way. But really what I'm saying is, do it both ways. You know, do it both ways. Okay, last one. X squared plus 9x plus 18 over 4x minus 20. Okay, now what are we looking at here? What's our argument? The argument is a rational. It's a rational expression. It's a rational equation, right? We have a rational equation. And therefore, what will our graph have? What was the information on bottom? The vertical asymptotes. And what was the information on top? X-intercepts. Yeah. And this particular one, because the exponent on top is bigger than the exponent on bottom, will have a slant asymptote. Let's try to piece that together real quick. The bottom is really 4 times x minus 5. Therefore, I have a vertical asymptote at 5. So there's my vertical asymptote. The top was x squared plus 9x plus 18. We just solved it, x plus 3, x plus 6. Therefore, it has x-intercepts at -3 and -6. So far, that's what we have. Also, there's a slant asymptote. If I actually took the time to do 4x minus 20 and do the long division of x squared plus 9x plus 18, which I will because it won't take that long. What do I multiply by 4x to get x squared? 1/4 x, and then I multiply that over, and that'd give me x squared minus 5x. And then I change the signs and add, so that'd be 14x plus 18. And what do I multiply by 4x to get 14x? Gosh, that would be like times 7 divided by 2. So 7/2 maybe? Yeah, that's it. So there's my slant asymptote. Let's check. Let's check, right? This is a nice little review of a rational expression. Let's go ahead and graph the original. So that's x squared plus 9x plus 18. Divide by 4x minus 20. And take a look. Does it have a vertical asymptote at 5? Let's check. X equals 5. Does it? Yeah, it does. Does it have x-intercepts at -6 and -3? It does. And furthermore, does it have a slant asymptote at, let's see here, 1/4 x plus 7/2? Whoop, I did that all wrong. Oh! Why would it have done that? Oh no, what happened? Well, what was my vertical asymptote? 5. How did everything get changed? Oh, 20. There we go. All right, and then it's 0.25 x plus 3.5. Bam! So folks, is that my slant asymptote? Is it my vertical asymptote? Is it my x-intercepts? So there's all the features that we predicted from studying what we studied before about rational functions. And so therefore my graph really looks like this. Oops. And down. And then up. Okay, well, in any case, those are all the features we have. So what's the question? When is the argument? When is the argument greater than 0? When is it above the x-axis? So when is it above the x-axis? First of all, it's above the x-axis everywhere over here, right? So from 5 to infinity, it's above the x-axis. What about over here? Did I have a little teeny blip where it was above the x-axis right there? Let's look. Where was it above the x-axis? Between -6 and 3. So what's our answer then? We are above the x-axis from 5. Actually, no, not at 5, but going from 5 over. And then also between -6 and 3. There. So that would be our domain for this particular one, because we asked when is that rational expression above the x-axis, and it was above from -6 to 3, and above everywhere to the right of 5. And so we would say our domain is -6 to 3, union 5 to infinity. Now, how can we check our answer? Just actually take the log of that thing and look at the graph. Ooh. Look at the graph. How fun is that? So where does the graph exist from left to right? Let's look at this piece first. Where does the graph exist from left to right? Yeah, from -6 to -3. And then where does the graph exist over here? To the right of 5. So isn't that interesting? Both approaches gave us the exact same answer. We either just look at the log graph directly and see where the graph exists from left to right, or we analyze the rational function and asked where was it above the x-axis. That's some incredible flexible thinking if you allow yourself both alternatives to ask when is the argument above the x-axis, or simply graph the log and say, where does it exist from left to right? And both of those strategies will work. All right, so there's some domain questions. Now, folks, I have to admit, for this next part, let's just look at it together. You don't necessarily have to make a fancy graph. I'm really interested in us just applying the rules of graph transformations that we previously talked about, because we just want to see how graphs get transformed. And let's review real quick, how do graphs get transformed? Because I think we're only going to be doing shifts of up, down, right, left. At least that's the only ones that I'm really interested in. So recall, if you had a function like this, what does the number outside the function tell you to do? Up and down, the way you'd expect, right? So this number is up and down, the same as your expectations. Whereas this number inside, okay, this is inside the function, that's right and left, but the opposite of what you'd expect. Right? So this particular parabola would be shifted up 3 and right 2. So let's take a look here. They're saying, consider number 1, consider the root function f of x equals 2 to the x. So what does that graph look like? Everybody just make a quick little sketch. It's an exponential function. Looks like that. Got an asymptote to the left and it blasts off to the right. So then what will our f of x equals 2 to the x minus 1? First of all, are we subtracting 1 outside the function or inside the function? Outside. So the minus 1 means shift the whole thing down 1. So in that particular case, if we shift the whole thing down 1, you're just taking your whole graph and you're shifting it down 1. So the whole thing just gets bumped down by 1 unit. Perhaps that'd be helpful to see on Desmos. So on Desmos, I've got 2 to the x, and then I've got the graph 2 to the x minus 1. And it's not incredibly compelling. I mean, it's just the same graph, and it got shifted down 1. So really, what got shifted down 1? The horizontal asymptote. The horizontal asymptote got shifted down 1. So whereas the original graph was approaching the x-axis, now the second graph is approaching the line -1. Yeah, there you go. Now you can see. The first graph is approaching the x-axis. The second graph is approaching -1. Same thing goes for this next one. Take a look at number 2. So we're just looking for a verbal description, folks. You can just say, shift down 1. So number 2, we have the parent function. We refer to the parent function as whatever the original function is that is unaltered. So that's our parent function. It's 1/3 of the x. So what did we do to this one? 1/3 to the x minus 1. Where are we subtracting 1? Outside the function or inside the function? It's inside the function. We're literally subtracting it from x itself. This one, we are subtracting it from the function 2 to the x. So that's outside. Whereas this one, we're subtracting 1 from x itself. So that's inside the function. So what does that mean then? If we're subtracting 1 to x itself, that means we actually move to the right 1. So this whole thing is shifted right 1. So let's take a look at that. We've got 1/3 to the x, and then we've got 1/3 to the x minus 1. Oh, I wrote -1 in the wrong spot. There we go. So this is kind of, nope, it still did it wrong. I better write x minus 1. All right, there we go. So do you agree if this is the original one, watch closely, that's the original, did it shift to the right? Did it get shifted to the right? Can you tell? Yeah, it did. It got shifted to the right. Okay. So now, if you turn the page, you have to turn the page? Yeah, you have to turn the page. Now they're giving us some graphs of log graphs. So let's just become familiar. If an exponential function, looks like this. So 10 to the power of x. Exponential looks like this, 10 to the power of x. Then what would the logarithm graph looks like? Since logarithms and exponentials are inverses, that's our symmetric line. So what should our log graph look like? Like that. And can you all turn your head and look and see that they're symmetric? So as we graph these logarithm graphs, we're going to be focusing on that shape. So folks, try drawing that yourself. Just as before, if you knew that an exponential graph would look like that, where the asymptote is over to the left, then a log graph looks like that, where the asymptote is now down on the y-axis. So you basically are taking that exponential graph and reflecting it mirror image-wise over the diagonal line. And now the asymptote is down here right along the y-axis, and it just starts moving up to the right. So that's what a log graph looks like. So when we look at a problem like number 5, it just says compare log x with log x plus 1. So there's log x. Now again, notice it says base 2. You can't do base 2 on Desmos or on your graphing calculator. So we're just looking at the shape of the graph. And so now we look at log of x plus 1. So in theory now, what just happened? Yeah. If our original graph was log x, and then our second graph is log of x plus 1, where did you add the 1 to? Inside or outside? This one's inside. And since it is inside, the plus 1, you really read that as left 1. So this graph got shifted left 1. So if you're looking at your original logarithm graph of coming up from the asymptote and going that way, you just shift it to the left 1. And now you come up from the asymptote and pick up that way. So the whole graph just got shifted to the left 1. There's not too much else to say about this. We're just talking about doing graph transformations. So let's just verbally describe these next few. In number 6, what did we do? We have log of x compared to log x plus 1. So is that plus 1 outside or inside? Yeah, it's outside, and therefore the plus 1 means up 1. So that's it. They're just saying that in number 6, the function of log base 1/3 of x plus 1 just means that you shift up 1 compared to the parent graph, because you're adding the 1 outside the function. How about in number 7? In number 7, they're saying consider log x, and then compare that to negative log x minus 2. Now we have 2 transformations. I didn't review that one with you. What happens if there's a negative sign up front? Yeah, flips upside down. That's kind of fun. So what does that mean now? Yeah, we're going to flip it upside down, and we shift it right 2, because it's inside the function. So what would that look like? You always start by drawing the parent. So the parent is vertical asymptote coming up from y, and then go to the right. I'm going to flip it upside down and shift it right 2. So I'm going to go right 2, tick, tick, to 2. I'm going to flip it upside down. So now my vertical asymptote is coming down from infinity. And then it just takes off that way. Two is now my vertical asymptote. The vertical asymptote shifts 2 units to the right. And then I flipped it upside down. That might be helpful to see. I have log x, and then I'm going to flip it upside down and shift it to the right 2. There. Is that what we drew? Essentially. Ooh, the last one's a good one. How about this last one? Now, folks, this last one says negative ln of 8 minus x. So let's say a few things about that. What's the definition of ln?
Here's some information.
Here's some information. The definition of ln? Log base e. Does the base in this case really matter? in terms of our graph? No. Now, here's a bigger question. 8 minus x. That's not the way we normally write it. We normally write things like x minus 2. So first of all, how do I rewrite this? Yeah, I'm going to write negative x minus, or x plus 8, right? So you have to switch those two around, so it's really negative x plus 8. But furthermore, and this is a transformation that we didn't really cover in detail, but you can't have a negative on the x. So you actually factor that out. Should this up here. And so that would become negative log base e of negative x minus 8. So do you see what I just did there? Remember, that's a leading negative. And when you have a leading negative, you have to factor it out of the whole expression. So since that's a negative 1x, I'm going to factor a negative 1 out. I can put that as a negative 1. Leaving behind x minus 8. Now I can read what remains. So this negative means flip upside down. This is outside the function, and outside the function is vertical movement. This negative 8 means right 8. And then finally, again, remember the distinction. If you're outside the function, it's vertical motion. If you're inside the function, it's horizontal motion. So a negative sign outside means you flip it upside down. A negative sign inside means you flip it right side left. So that part right there means flip right side left. Why don't we have that word in our English language, let alone Spanish or German or any other language? We say flip upside down all the time, right? They're like, no, flip it upside down. And so that's part of our language. But do we ever say things like, would you please flip that right side left? We never do. And why is that? It's kind of because, isn't it impossible? I mean, look at my face. Can I flip my face right side left? I really can't. I mean, I can turn around, but you're not looking at my face anymore. So can I flip even this paper right side left? If I do, you're no longer looking at the paper. You're looking at the back of the paper. So can we flip things right side left in our physical reality? You kind of can't. What you can do is turn it around. You can turn things around, but you really can't flip things right side left, can you? Isn't that weird? You can flip something upside down, but you can't flip it right side left. And yet, folks, when you look in a mirror, what does it do? When you look in a mirror and you're looking at your lovely smiling face, what did the mirror do? It flipped it left side right, right? Like you've known that your whole life, that when you look at your face in the mirror, that's not actually the face that anyone else sees. Right? Have you ever actually seen your non-reflected face? And you're like, oh my gosh, that's what I look like? Because you spend your whole life looking at your face right side left. That's the only you know, is the right side left you. And all the rest of us know the other you. Isn't that weird? Isn't this trippy? It's strange. If you haven't had a chance to look at your non-reflected face, you really should. Of course, when do you see your non-reflected face? Yeah, any photograph, right? Compared to your face in a mirror versus a photograph. That's flipping right side left. Okay. I just, you know. All right, moving on, folks. 6.2, we're looking at properties of logarithms. Now, properties of logarithms, we're definitely going to want to write down some rules. Yeah, before we jump right in. Now, again, they list out a whole bunch of rules up there. They're all fine. They're wonderful. I don't necessarily like the way that they wrote them. So I'm going to have us write down our own rules on the next page. Now, on this page, I don't know that you really have enough space to write down the rules. I think you should take out a sheet of lined paper. And let's write down log properties. Oh, that's what I was going to say. Isn't this weird, though? When you look in a mirror, because I still don't understand it myself. When you look in a mirror, it does automatically flip your face left side right. And yet it doesn't automatically flip you upside down. Does anyone understand that? What should that be? Why should a mirror automatically flip you left side right, but it doesn't flip you upside down? Yeah, weird. I mean, surely there's an easy answer, but I don't know. Like I'm thinking it's because our eyeballs are left and right. But I mean, if I just turn my head, that's still not flipping me upside down. So you got me. All right, so everyone has a sheet of line paper. Oh, folks, it just occurred to me, we do have a word for left side right. What's our word for flipping something left side right? I think it's just called looking at the mirror image. If you look at the mirror image, that's left side right. And so that's what we would call it. If you wanted to see something flip left side right, you have to look at the mirror image. Okay, here we go. Log rules. So go right up at the top. Log rules / properties. Now, first of all, if you wrote that down this way, logs rule, that means something slightly different. That would imply you have some enthusiasm for logarithms. We're talking about log rules. So here's our log rules. The first thing is that if you have log of A times B. Okay, now, what's our base? Doesn't matter. The base doesn't matter. The base is whatever the base is. If it's base 8, then fine, it's base 8. If it's base 10, we'll just go ahead and assume it's base 10. That way we don't have to keep on writing the base. So all we're going to do is write log, and that implies log base 10, the button on your calculator. But just so you know, all these rules work regardless of what the base is. So it could be base 2, it could be base 10, it could be base E, it could be base 10. So first rule, this is called the product rule. Log of a product, log of A times B is really log A plus log B. Now that's really surprising. And the first time you see this, that's very surprising. The log of a product is the sum of the logs. So as an example, if I had log of 10 times 10, then that's actually equal to log 10 plus log 10. So you can break up a product and turn it into addition. That's pretty weird. I don't think that we have a rule like that in another part of life. Because remember, like when you do a square root of 20, then that's really the square root of 4 times 5, and that becomes the square root times the square root, right? So previously we have broken up a root of multiplication into more multiplication. Just think of how weird it would be if we took root 20, turned it into root 4 times 5, and then it became root 4 plus root 5. That'd be weird, right? And your brain would kind of rebel against that. Like, why on earth would that happen? And yet, that's exactly what we're saying here. That the log of a product is the sum of the logs. And let's just check it. You know, let's check real quick. You don't have to write this down, but check. This is really log of 100. And then that's log 10 plus log 10. We can all answer this question right now. 10 to the what is 100? Yeah, 10 to the what is 100? 2. And 10 to the what is 10? 10 to the what is 10? 1. And so yes, 2 equals 2. So it's true. So that's just one quick example for you to see that. So there's the first rule. Second rule, if we have log of a product, we'd also like to have log of a quotient. Log of A divided by B. What's your guess? Yeah, it's going to be log A minus log B. So log of multiplication turns into the addition of logs. Log of division turns into the subtraction of logs. I want you to notice something here. The numerator is positive, technically. The denominator is a negative log. That's helpful to note. Now when you have log of a fraction, the numerator is a positive log, and the denominator is a negative log. We call it subtraction, but really anything in the numerator becomes a positive log, and anything in the denominator becomes a negative log. So it's helpful to think of it that way. Okay, so that's our next rule there. We could do a quick example, something simple to make it obvious. We could do log of 100 over 10. This is just an example for you to see. So log of 100 minus log of 10. You don't have to solve it all the way here, but first of all, 100 divided by 10 is 10, and log base 10 of 10 is 1, because 10 to the 1 is 10 to 1. And over here, 10 to the 1 is 100, 2, and 10 to the 1 is 10 to 1, and sure enough, 1 equals 1. So the rule does work. Okay, so that's our product rule. If you wanted to label it, product rule. This is our quotient rule. And then we have a power rule as well. So if you have log of A to the power of n. what happens is the exponent just comes out front and gets multiplied. Oops, sorry, that doesn't come out. And I'll even draw a little arrow to make it more obvious. The exponent gets multiplied out front. Just the exponent. And that's the power rule. As an example, let's say you had log of 10 squared. Well, 10 squared is 100. 10 to the what is 100? 2. Or I can take the 2, bring it out front, and that's 2 log 10. And log of 10 means 10 to the what is 10? That's 1. 2 times 1 is 2. So it does work. All right, so folks, those are our 3 log rules. One more thing to say. So what can we take the log of? A product. We can take the log of a quotient, and we can take the log of a power. Okay. What can we not take the log of? The log of a plus b is equal to nothing. There's no way to rewrite it. It's just log of a plus b. It's not simplifiable. Okay, nobody can read that because I just wrote it. I'm going to put some more notes back here. Okay. I'm sorry. So yeah, this thing is not simplifiable. Log of a plus b is just log of a plus b. There's nothing you can do to it. Likewise, another thing you cannot do is log of a minus b. That is not simplifiable. So taking a look at our board there, which one of those is not simplifiable at face value? Which one? Yeah. At face value, this one's not simplifiable because you can't do the log of a subtraction problem and rewrite it in some other way. Okay. So there are no rules to simplify those. Only the log of a product, quotient, and power can be simplified. And really, the word simplified is perhaps not the best word. Rewritten. Okay. You can rewrite the log of a product. You can rewrite the log of a quotient. You can rewrite the log of a power. You cannot rewrite the log of a sum or the log of a difference. Okay, everyone has your rules? Let's apply them. Let's try number 1. This one says log, and again, it doesn't matter what the base is, 1,000 x cubed y to the 5th. Now, what we're about to do is not simplifying, it's rewriting. We're simply going to rewrite it in a different way. Kind of like, and this is a terrible example, but let's say that I had the number 2,496. I could rewrite that as 2,000 plus 400 plus 90 plus 6. And you might say, why on earth would you do that? Well, because you can. Okay? Rewriting is just something you can do. You know, there's power in being able to rewrite something. For instance, you can also rewrite x squared minus 25 as x plus 5, x minus 5. Right? We're not necessarily saying that we're simplifying anything. We're just rewriting it. Because there's power in rewriting something in a different way, to reconceptualize something. Okay, so in this case, what we really have, and everyone write this with me, we have log of a product. So that's 1,000 times x cubed times y to the 5th. So what does that mean? Anytime we have a product, we can rewrite it as addition. So we can rewrite this now as log of 1,000 plus log of x cubed plus log of y to the 5th. Now I realize we only wrote the rule down as one single product, but it doesn't matter how many numbers are being multiplied. So since we have a triple product, we can rewrite it as a log plus a log plus a log. Okay, now what can we do? Like, what's log of 1,000? You should all be able to answer this. That's base 10. We're assuming it's base 10. 10 to the what is 1,000? 10 to the what is 1,000? Helps to write it down. 10 to the what is 1,000? Yeah, 1,000 is 10 to the 3rd, and therefore same base, x1 is going to be equal. 10 to the 3 is 1,000. Therefore, log of 1,000 is just 3. Now, even though we're just rewriting, I think we'd all agree that's simplified. I'd rather look at the number 3 than look at the number 1,000. Okay, now what about this one? What can we do here? What rule will we apply here? What rule would we apply? Is it a quotient? Is it a product? Or is it a power? It's a power. So what can we do with that 3? You can drop it down out front. That's 3 log x. Same thing goes with the last one. You always want to ask yourself, what rule would I apply? Is this a product, a quotient, or a power? If this is also a power, so I can drop my power up front, and I get 5 log 1. So folks, what do you think? We certainly did rewrite it. Would you feel like saying that we simplified it? I mean, maybe. On the one hand, this is just 1 log expression, but the numbers are big and they're powers. Whereas here it's 3 log expressions, but the numbers are very small, and there are no powers. The bottom line is it's definitely rewriting, whether you consider it simplifying or not simplifying. We call this one the condensed form, and we call this one the expanded form. So we started with the problem condensed, and then we expanded it using log rules. Now, as you approach problems like this, whether you condense an expression or expand an expression, you want to stare at it and ask yourself, what rule can I apply? Product, quotient, or power? And you typically go in a particular order, and that order would be, just kind of, well, it really depends. Let's talk about that. So let's look at number 2. In number 2, we have log. Now I'm going to say something a little crazy here, folks. I realize it says log base 5. Does the base matter? Not necessarily. I mean, we could just start expanding the whole thing, not worrying too much about the 5. But I will go ahead and write it down. So it's log base 5 of z over 25 to the 3. Okay. So let's talk about this in a couple days. This is condensed. We'd like to expand it. Do we have a product anywhere? No. Do we have a quotient? Yeah, z over 25. Do we have a power? Yeah. What should we do first, the quotient or the power? I would say probably, in this case, the power. If you think of it as PEMDAS, what's happening to z? Z is being divided by 25 and raised to the power of 3. So the last thing you said was power of 3, so probably do the exponent first. And let's go with that. So first things first, apply the power rule. And the power rule says you can bring that 3 out front and rewrite it there. So now we have 3, and I'm going to put brackets, log base 5 of z over 25. Why did I put brackets? Because we're about to proceed to expand this even further. So now, looking again, what rules do we have? Do we have a product? No. Do we have a quotient? Yes. Do we have any more powers? No. So just the quotient now. So how do I rewrite a quotient? Yeah, so now this is log base. Now remember, numerator minus denominator. Helpful to think of it. Numerator minus denominator. Just like we read top to bottom, we're going to write it down as numerator then denominator. So anything in the numerator is a positive log, so that's log base 5 of z. And then minus the denominator, log base 5 of 25. Now, right now, this is expanded because we don't have any more rules to apply. There's no more products, there's no more quotients, there's no more powers. But since it is base 5, we can actually simplify this one. So you can all do this in your head. 5 to the what is 25? 2. So now that's 3 log base 5 of z minus 2. Now, the last thing that you could do, and depending on your perspective, I would probably distribute the 3. So then I would simply have 3 log base 5 of z minus 6. And that's expanded and simplified as much as possible. Now let me ask you, we certainly rewrote it, okay? we rewrote this condensed expression as an expanded expression, would you say it's simplified? And keep in mind that the word simplified means better, right? Fewer computations, less rigorous computations, computations you could do more easily. Is it easier to do this computation or that computation? Yeah, maybe I would say probably the bottom one, because this one you have to cube and divide. Yeah, exactly. So here you're going to divide something and cube it, and cubing makes numbers pretty big or complicated anyway. Whereas here, all you're going to do is take the log of the single number, and then you times 3 and subtract 6. So I'm going to say this one is actually simplified. You know, I'll go out on a limb. You might disagree with me philosophically, but we did rewrite it, we expanded it, and I think it's even simplified. How about number 3? We have natural log of root z over xy. One thing we've talked about today is using definitions to rewrite things. How should I rewrite the square root? Yeah, just z to the 1/2. Yeah, and why do we want to rewrite it as a power? Well, because we have a power rule. We do not have a root rule. So we want to rewrite that first and foremost. So we have natural log of z to the 1/2 over xy. And now we're looking at this, and let's run through the rules. Do we have a product?
Oh, yeah.
We do have a product. Do we have a quotient? Yeah, we have a fraction. Do we have a power? Yes, we have all 3. So what's the correct order to do it in? Well, if you try to do the power first, you can't really, because the 1/2 is not on the whole thing. The 1/2 is only on the z. So I can't pull the 1/2 out because it's not also on the bottom. The product, it's stuck in the denominator right now. So I can't really do the product either. If you have a quotient, that's usually the starting point. So we can go ahead and do the quotient, which is simply numerator minus denominator. So let's rewrite this now as natural log of numerator minus natural log of denominator. Oh, you mean log IC? Correct, you don't have to. Yeah, we can just leave it as ln. Okay, so now what can we do? Let's look at the first one first. What rule applies? Yeah, the power rule, so we can drop that 1/2 out front. So now I have 1/2 natural log z. Now, very careful here. We have a minus sign, and we're about to subtract natural log of a product. Now, what does a product turn into? It turns into a sum, but we're subtracting a sum, so we need to very carefully put parentheses here. So that when we write natural log xy as natural log x plus natural log y, we need to remember that we're subtracting the whole thing. So that means we're going to distribute the minus. And now we're done. So it's 1/2 natural log z minus natural log x minus natural log y. Now I'd like to call your attention real quick that it could have been possible for us to go straight from here to here. Not that you have to, but I just want you to notice. Any term in the numerator is going to be a positive log. And sure enough, this is natural log of z. Is it positive? Yeah, it's a positive log. Sure, I brought the 1/2 out front, but it's a positive log. And I said any term in the denominator is going to become a negative log. So did the x become a negative natural log x? Yeah. And the y is also in the denominator. Did it become a negative log? Yes. So essentially, when you see an expression like this, you could immediately say any term in the numerator is going to be a positive log. Any term in the denominator is going to be a negative log. It's just a simplifying rule. You can use it or not. Okay, number 4. We said, number 4, there was no rule that applied. So that's log base 5 of x squared minus 25. Do we have a rule for log of a difference? No. So at face value, you say, okay, I can't do anything with that. But what could we do with x squared minus 25? And now just notice, this is a really powerful thought here. We're looking at this saying that's a subtraction problem. There is no way to simplify a subtraction problem. But we happen to know of another definition that allows us to rewrite a difference as a product. Okay, so I mean, so much of mathematics falls back on just, do you remember lots and lots of rules? Like this particular rule. So now we can rewrite that as log base 5 of x plus 5, x minus 5. And now we do have a log of a product. And so now we can rewrite that as log base 5 of x plus 5 plus log base 5 of x minus 5. So we turned a subtraction problem into a multiplication problem, which allowed us to use a log rule to rewrite it. Now, that's an addition problem. Do we have a rule for addition? No. Do we have a rule for subtraction? No. Okay, so now we're done. Now, you look at that and you say, is it simplified? Well, I don't know. You know, what do you prefer? The first one or the last one? Not sure. The fact is we rewrote it. And sometimes there's just value in rewriting. Okay. We're going to do number 5, 6, and then where does that leave us? All of these problems were expansions, and now look on the next page, they're all condensing. Oh, and then we'll get to the change of base, and then we'll do all that. Okay, wonderful. Well, yeah, let's finish this, and then we'll take a break. So, I mean, not a break, it's stop. Okay, number 5. I'd like you all to try this out with me. This says log base 3 of x squared over 81 y to the 4th. Okay, everybody try this out with me. I've suggested it a couple times, but let's do it directly. Any term in the numerator will be a positive log. Any term in the denominator will be a negative log. So we can immediately take this and rewrite it, the x squared as a positive log base 3 of x squared. The 81, we can immediately write as a negative log base 3 of 81. And the y to the 4th is in the denominator, so I can rewrite it as a negative log base 3 of y to the 4th. So you'll notice I didn't kind of go step by step saying, okay, it's a quotient, so I'll rewrite it as a subtraction, and then I have a product, so I'll rewrite it as a plus. I could have done that, just like we did this one. This one. Yeah, we could have done it this way, but I wanted to show you another way. So now what? I can now simplify each and every one of these. So here, what rule still applies? Yeah, I can drop that power out front. Over here, I have a power, I can drop that one out front. So that gives us 2 log base 3 of x. And then this one, you could all do in your head. So if you look back at that very first page where we did a bunch of powers of 3, again, I encourage you to be memorizing those. That would be 3, 9, 27, 81. So 3 to the 4th equals 81, so that's just a 4. And then this one, you can drop that power out front, and it's minus 4. And that's expanded. Whether you consider it simplified or not, it's expanded. Okay, last one, number 6. I'm going to write it just as it is. Natural log of the 4th root of xy over ez. E is not a variable. E is the constant 2.71828182. Okay, so what's the first thing we would do here? You can think about, okay, what rules apply? Is there a product? Yes, xy, easy. Is there a quotient? Yes, there's a fraction. Is there a power rule? Kind of. But so the first thing we'd want to do is rewrite that 4th root as xy to the ez. That's 1/4. Now again, you'll notice this 1/4 is on the entire thing. So I can apply the power rule and bring the 1/4 out. So we're going to drop that 1/4 out in front. And so now it's 1/4 natural log of xy to ez. Notice we're only allowed to do the power rule right now, the 1/4, because the 1/4 was over the whole thing. Remember over here, the 1/2 was only on the z. So I couldn't bring that out of this expression yet, because it was still over a denominator. Okay, so now what? We've got xy over ez. Again, I would apply the rule that anything in the numerator is a positive log, anything in the denominator is a negative log. So that's going to be 1/4, big bracket, and that'd be natural log x plus natural log y minus natural log e minus natural log z. Again, any term that was in the numerator became a positive log. Any term in the denominator became a negative log. And what's the last thing we can do? These are just variables, so there's nothing we can do. But what's the natural log of e? Don't shout it out. What is the natural log of e? How would you find out? How would you convince yourself what the answer is? What's natural log of e? Our first strategy we learned today was if you don't know something, call it x. And natural log, by definition, is log base e of e equals x. This is log form converted to exponential form. Left to the right equals middle. E of x equals e, which is technically e to the 1. Same base, exponents must be equal, so x equals 1, and therefore natural log of e equals 1. Right? That's how you'd walk your way through something. Or you can just type it in your calculator. So what do we have then? Natural log x plus natural log y. I'm going to minus the natural log z first, and then minus 1. And probably this time I won't distribute the 1/4. I mean, you could. It would just look a little awkward to constantly have 1/4 natural log x plus 1/4 natural log y minus 1/4 natural log z minus 1/4. And you certainly could. Both of those would be fine. All right. So folks, where does that leave us? Today's Monday. When we come back, we'll condense these expressions. Boy, I wish we had the time to do it now. And then we'll start learning one last critical rule called the change of base formula. And that will allow us to solve lots of exponential equations. And then we'll be able to solve log equations. And then we'll do some application problems. Yep, that's where we're at. I don't think I have anything to pass back to you. What time is class end? 10:20? Oh, really? Okay, so a minute ago. Okay, go ahead. For a second there, I thought I had 5 more minutes. Folks, if you have any questions, please.